Hi, my name is Gabriel Moreira, and in this presentation I'll go over our paper VICAN, Very Efficient Calibration Algorithm for Large Camera Networks. So let's dive in. Post-graph optimization, or PGO, is a well-established approach used in SLAM and in the calibration of camera networks. It works by synchronizing or averaging a set of pairwise rigid transformations between cameras, and this is done by solving a non-convex optimization problem. Since PGO only redistributes the errors of the graph, the camera poses can only be as accurate as the pairwise measurements, so to speak. This is thus problematic in scenarios where it may be difficult to establish accurate point correspondences between images. Examples of this are applications in smart retail, which often include cluttered and occluded indoor environments. What we propose to do then is to augment the traditional PGO formulation with additional notes, corresponding to a rigid object moving in the scene. The set of edges between the cameras and the objects over time form a bipartite pose graph, which we solve instead. We introduce a new algorithm for this bipartite PGO problem and a new 3D dataset to benchmark it. Let's go over the problem in more detail. We consider a network of cameras and an arbitrary rigid object such as the cube represented here on the left. The condition we place on this object is that we assume that we can perform monocular pose estimation, for example, via perspective endpoint if the object is covered in Aruco markers. The object is then free to move around in the scene, and at each time step, and for the cameras with the object in their field of view, we record the pairwise camera-object relative transformations. What we obtain is the bipartite graph, and the goal is to estimate the pose of each of the cameras given the set of camera-object transformations, that is, the edges of the graph. The idea is that as the object moves around, we're able to average or integrate more transformations, and thus improve the camera pose estimates. In order to do so, any PGO framework could be employed. However, we can take advantage of two things. First, we're only interested in the camera poses, and second, the fact that the graph is bipartite. So let us delve into our proposed approach. The general setup is depicted on the right. We have a set of camera nodes, which are the circles, indexed by C, and a rigid object, which itself may have M nodes indexed by M. The object is free to move around for time t, and we can check that on the image, the object is shown in two different poses at times t equals 0 and t equals 1. Under Gaussian noise in the translations and Langevin noise in the rotations, the negative likelihood includes two terms as shown below. Here, we use a well-known approximation whereby we solve the non-convex rotations term on the left first, and then plug the resulting rotations in the least squares problem corresponding to the rightmost term. The problem corresponding to the leftmost term is known as rotation synchronization and admits the primal dual characterization shown here. Namely, we define block matrices for the data, written R tilde, and the variables, written R, which include the block RC containing the camera rotations and the block RT corresponding to the object rotations. The dual variable is denoted by lambda and similarly includes the block lambda C for the cameras and lambda T for the object. Since the number of time steps T can be quite large, solving the primal via the dual STP can be expensive. So the algorithm we propose is as follows. We first initialize the object's dual variable via the graph degree matrix. This is known as the spectral initialization. Then we proceed iteratively. We fix the object's dual variable and solve for the camera rotations. And this is just a standard rotation synchronization problem. Then we re-estimate the object's dual variable via a step of the Frank-Wolf iteration. The reason why we split the iterations this way is that t can grow to be much larger than the number of cameras. So using Frank-Wolf in step 2 allows for a much cheaper update. Let us now see how this algorithm performs in practice. We conducted our experiments on a new 3D dataset of indoor scenes that we've developed and are releasing with this paper. The large shop, as shown here, is one of those 3D scenes. It's a realistic model of a supermarket sprawling over 350 square meters and covered by 342 cameras, whose locations are shown on the right. Here are some examples of images from the large shop data with the object that we have selected, a cube covered in 24 Aruco markers. Let us now look at the results. The two box plots correspond to the angular and translation errors with respect to the ground truth camera poses. As expected, the errors go down as the number of time step increases. In fact, notice that the median rotation error is just below 0.04 degrees when considering over 5,000 time steps. The algorithm converges in 2 iterations, thus yielding the estimates in just above a second in our Python implementation. Here's a top-down view of the shop. Ground truth poses are shown in red and our estimates in blue. In the second scene, entitled Small Room, we have a 72 square meter room covered by 25 cameras. Once again, here are some renders obtained from 4 of the cameras. And now the results. In this scene, we observe a similar phenomenon, namely, the error goes down as we increase the number of object poses. Median error of 1 centimeter for over 500 steps with a time per iteration of slightly above 0.2 seconds. Here's the top-down view of the estimates versus the ground truth. And so, to conclude, we presented a formulation of camera network pose estimation as a bipartite PGO problem and introduced a duality-based algorithm to solve it. In addition, we released a new benchmark dataset. All the code, 3D models, and renders are available, so do make sure to check it out on the project repository. Thank you.